right, welcome to the very last machine learning lecture. Congratulations, you made it another semester. So today we're going to finish up with boosting and then do hidden Markov models and some approximate inference methods. So let's get right down to it. So you remember from last time, our goal was to learn a voted classifier, right? So if you remember from bagging, right, we had the idea that we would train a whole bunch of classifiers and then vote them to hopefully get a more accurate answer than any one classifier. And then boosting was the idea that, well, as long as we're looking for a voted classifier anyway, why not train the voting weights by maximum likelihood or maximum conditional likelihood? And so we had just gotten through setting up the problem, and I'm going to review that setup. But if you remember, so each classifier is a function. We're thinking of it as a function now from k-dimensional real vectors to plus or minus 1, right? So just an ordinary binary classifier. Voting a classifier means summing up a whole bunch of classifiers, right, and counting whether more of them say plus or more of them say minus. And then a weighted vote, you have weights alpha for each one of the voted classifiers. And without loss of generality, we can assume that all of the weights are positive, because we can assume that if a classifier is in our hypothesis space, then the negation of that classifier is also in our hypothesis space. So we'll pick the one where the weight would be positive. And so this space of voted classifiers winds up being substantially more expressive. So a good example of that is this 5-pointed star here. So what happened is that I took 5 half-space classifiers and a constant classifier and voted them all together, and I can get something that says yes anytime you're in this star-shaped region, right? Which is clearly a fancier hypothesis class than we could have gotten with just the plain original half spaces. All right. So in order to set up the optimization problem, we put together this matrix that I was calling Z, like that, and so. You know, a particular element here, right, is going to be, we'll call that Zij, right, for example I and classifier J. And because it's a -1, that means that example I was classified incorrectly by classifier J, right? So the fourth example in the second classifier, that classifier got that example wrong, right? So it makes sense what this matrix is. Yes? And what we were thinking of doing then was getting a bunch of weights, alpha 1, alpha 2, and so forth, right? And then the voted classifier will get an example right if and only if more of the individual classifiers, according to their weights, get it right than get it wrong, right? Which is to say that the sum of, you know, alpha j times Zij has to be bigger than or equal to 0. Right? So I'll write that down, right? What we want is for the sum over j of alpha j Zij, right? What we want is for that to be bigger than 0. And if that's true, then we're going to get the example right. And if it's not, then we'll get the example wrong, right? And this was just a matrix multiplication, right? Z times alpha if we collect all of the weights into one vector. And so our optimization problem is going to be to find that alpha. All right, so just so that we have that same thing in equations, right? So our weighted vote is going to be sum over j of alpha j fj of xi, right? And then if we multiply yi by that weighted vote, that'll be positive if we get it right and negative if we get it wrong, and that's this matrix multiplication. Right? So that's just Z times alpha. And now what we're going to do is we're going to assume a logistic model, right? So we're going to assume that the log probability that y is true given x is just h of s, right? And so that's this thing here. Sorry, I guess I should say it's h of. Yeah, this is the log of the probability that yi takes its observed value, right, is going to be h of s. So this is a logistic model. And then maximum conditional likelihood just means sorry, this is the negative log probability. So we want to minimize this function L of alpha s, which is just the sum over all examples of the negative log probability of that example, right? So if we succeed in doing this, then we will have found the best possible voted classifier in terms of maximum conditional likelihood. All right? So going back to here, right, this matrix is ridiculously large typically, right? So we might have 1 million training examples, and then there could be as many as 2 to the million different classifiers on those training examples. So we are not going to be writing down this matrix. But at least conceptually, if we can solve this optimization problem, then we'll do a good job. All right? So everybody happy with the setup? All right. So what we're actually going to do is a really simple optimization algorithm called coordinate descent. So what is coordinate descent? Coordinate descent, so we're going to do coordinate descent on the alphas, right? And what that means is we find a component of alpha such that changing that component of alpha can improve our score, right? So in particular, the derivative of the negative log likelihood with respect to alpha j is negative, meaning that if we increase alpha j, we're going to improve our log likelihood, negative log likelihood. And so we just keep finding an index such that that's true and upping the weight of that index, right? So it's a really, really simple algorithm. And we keep doing that until we're tired or until we stop being able to improve, okay? And so since we had, I introduced the terminology last time of a weak hypothesis. So a weak hypothesis is just one of these columns, right? Just a single classifier. That's to distinguish it from the voted hypothesis at the end that we're trying to get. So what this is we're selecting a j, which corresponds to one of our base classifiers, a weak hypothesis, and we're increasing the weight of that one, right? And hopefully we select a good, a useful one to include in our vote. All right? So and of course, in order to make this fast, right, this step, the find an index, right, this step has to be efficiently implementable. We can't do it by enumerating all of the columns of this Z matrix, right? We can't do it by enumerating all of our classifiers. So let's take a look then at how we might do it, right? So this derivative, right? From this previous page, right? This was the definition of L, right? Was that L is the sum over I of h of Si, right? So minus dl d alpha is minus the sum over I of the derivative of, well, the sum end. So that's h prime of Si, right? Times then the derivative of Si with respect to alpha, right? Right? And we had before that S was equal to, I'll go back and take a look, right? S was just equal to Z times alpha, right? And so the derivative of Si with respect to alpha j is just the ij element of this matrix, right? So this is equal to the sum over I of minus h prime of Si times Zij, right? So let's take a look at this. So first of all, if you remember, right, h was sloping down like that, right? And so h prime was negative, minus h prime is positive, right? So this thing here, we can think of it as a positive weight, right? And Zij was whether classifier j got example I right. And so what we're looking for is a classifier such that according to these weights, we get as many examples right as possible, right? So these are weights on the individual examples. And what we're looking for is a single classifier that, according to this distribution of weights, gets as many examples right as possible, right? So that should sound like a familiar problem, right? This is the classification problem. So finding a good weak hypothesis is just a weighted classification problem, where the weights are selected according to this scheme here, right? You just figure out h prime of si, and that's the weight of the example. So the interpretation is basically, right, so if we look at minus h prime, right, that's going to be a function that looks like this. It'll start off at 1 and it'll go down to 0, right? So this is minus h prime. And so if the weight is big, that means we're getting this example confidently wrong. If the weight is small, that means we're getting this example confidently right. Right? And so what does this mean? It means we look at the examples we're currently getting confidently wrong. We put high weight on those, and we search for a classifier that does well on the examples we're currently doing poorly on. Right? And that's sort of intuitively a reasonable thing to be doing. Right? And so you get a very simple and appealing algorithm, right? You reweight your examples according to which ones you're getting right and wrong, higher weights going on the ones you're currently getting wrong. Then you pass that distribution, that set of weights, to your classification algorithm, learn a classifier with whatever your favorite classification algorithm is, and that gives you a good weak hypothesis whose weight you should increase in the vote. All right? Yeah? Right, so this was h, right? And so minus h prime looked like this, right? And s was the, s here, right, si was the sum over all classifiers in our current vote of whether that classifier was getting the example right or wrong, right? And so what's happening is that si will be very negative if we're getting most examples, if most of the classifiers are getting that example wrong, and it'll be very positive if most of them are getting the example right. So if we're very negative, the weight will be high, and if we're very positive, the weight will be low. For that particular example, that's right. So this is a weight for example I. Right? And there's going to be a separate weight for each example, and it's going to be based on whether that example is currently wrong or right in our vote. Okay? So it's a nice, simple, appealing algorithm. And just to summarize it, right? So, oh, I should say, by the way, this quantity here, right? This is called the edge of classifier J. And so what we're going to do for boosting is we don't want to make any assumptions about the form of our classification algorithm. All we want to do is assume that it's decent enough to do better than chance. And so what we're going to assume is that there's some small constant gamma such that the weighted classification algorithm finds a classifier that actually gets edge bigger than or equal to gamma, right? So in other words, we're not going to assume that we find the optimal classifier for our weighted distribution. We're just going to assume that we get the edge slightly above 0, which means we're doing slightly better than 50-50 for the classifier, right? And there's a famous theorem that says that if the weak learning algorithm always succeeds, in other words, if we always manage to get a positive edge, then the log likelihood goes to 0, right? In other words, we're getting so 0 means that we're very confidently getting each example right? So that is, that's an interesting theorem. It answered what was an important open problem at the time. So people were wondering whether, suppose that you had a classification algorithm that could do just slightly better than chance, would you be able to parlay that weak learning algorithm into a strong learning algorithm, one that could guarantee to classify your training set perfectly? And for a long time that wasn't known, and it was answered positively by this boosting algorithm. So it's kind of an interesting question, and it turns out to be an important technique in practice. All right. So I did this specifically for log likelihood, but in fact, this penalty function h of s could be any convex decreasing function of s. So for example, one common choice is e to the minus, well, now it's z instead of s. So s slash z slash s globally, right? For those of you who like Perl. So e to the minus s, right? And this leads to actually what was the very first boosting algorithm called AdaBoost. You could use hinge loss. What we used was the logistic hinge loss, right? Log of 1 plus e to the minus s. And that leads to a discrete variant of a boosting algorithm called logit boost. Another thing that we can do is instead of using just +1, -1 classifiers, we can use classifiers that are confidence rated. They give you a number between plus and -1. Or we can actually even let it doesn't matter what the range is, right? So we could use a log odds transform to get it to the range to be plus to minus infinity. Or we could actually even use a regression algorithm instead of a classifier in the inner loop of our boosting algorithm. Another thing that's maybe important is how to choose what is the set of weak hypotheses that we're using. So so typically, for example, if you're just using one decision tree, you'll often want to make a fairly big decision tree. But if you're using decision trees inside boosting, you'll want to make a much shallower decision tree. And then let the power come from voting together lots of these, right? And so it's just a heuristic, but this is something that people have observed in practice mitigates overfitting a lot, is that each individual weak learner should actually be pretty weak. So people often use decision stumps inside of boosting, which is decision trees of just one level. But you can use anything you want, but boosted decision stumps turns out to be a pretty powerful classifier. And people will often, instead of decision stumps, just use shallow decision trees. When you run this algorithm, in practice, it will actually typically take your error very quickly to 0. In theory, it could also stop when your weak learning algorithm fails, right? It could be that your weak learner can't find a hypothesis that has a big enough edge, but that actually doesn't happen. And if it does happen, you just switch to a slightly bigger weak hypothesis class. Even after the training error goes to 0, boosting will typically keep increasing the margin, in other words, the confidence with which you correctly classify all of your training examples. And that's actually an important point because this is usually given as the reason why boosting tends not to overfit. In other words, even though it's a very complicated hypothesis class, what you're doing is you're searching for a classifier with high margin within that complicated hypothesis class. And if you succeed in getting something with high margin, then you can show that overfitting is limited. Yeah? No, it wasn't a question? Okay. So one last point. It turns out that if your weak learner can always succeed, that shows that there exists a vote that gets every training example right. And that sounds like a strong assumption. If the weak learner can fail, boosting seems like an algorithm for finding a way to make it fail, finding a distribution that it can't succeed on. But in practice, like I said, it actually works well. Like you usually don't stop with the weak learner failing. You usually stop by getting everybody right with a high margin. All right. So questions about boosting? Yeah. Right. Oh, so overfitting does not mean that the training loss is equal to the test loss. What it means in this case is that, so like the typical plot with a learning algorithm, right, is that the training and the test loss go down for a while, and then the training loss keeps going down, and the test loss goes back up, right? So with boosting, what will happen is that the training and the test loss will go down. They'll separate, but both will keep going down, and the test loss won't curve back up at the end. Right? So that's what I mean by not overfitting. It won't mean that you get perfect classification of your test set. That would be too good to be true, as you point out.
So with boosting, you
Right. You typically, when you run boosting, you run it as long as you can afford the computation, right? Or as long as you can afford the, like, if you have an expensive classifier and you have, 1,000 of them that you have to evaluate at test time, that could get pricey as well. So you'll run it as much as you can afford, either at, with a training time limit or a test time limit. Right. And I don't want to say that, magically it can't ever overfit, right? Like if you keep on going, it is possible to have the training error curve back up. It's just an observation that it is much less subject to this than other forms of classifier. And the reason that people usually give for this is the fact that it keeps improving the margin. And so you're looking for a high margin classifier.
So we choose those like weight classifier, like it's just because it's easy to train, or?
So why do we use decision stumps as opposed to some other weak classifier? There's a bunch of reasons. One is decision stumps are very fast to execute, and so you can actually afford to boost together 10,000 decision stumps, and it won't be a problem on a modern computer. The other is that heuristically, boosting seems to perform better when it's taking smaller steps, which means when the weak hypothesis class is actually fairly weak. But that's just a heuristic, and there's sort of a, for any given problem, there's sort of a Goldilocks level of classifier. If you make it too weak, you won't make progress. If you make it too strong, you might actually get boosting to overfit. And somewhere in the middle, which is actually a pretty wide range, you'll get boosting to perform well. More questions about boosting? Yeah.
You said that boosting works particularly well for decision forests.
Boosting works particularly well on top of decision trees, partly because decision trees are very fast, partly because voting decision trees together improves their expressiveness a lot. So for example, if you have axis parallel splits and you vote a bunch of them together, you can get a diagonal line, right? But people will boost other classifiers as well. You could, for example, boost a perceptron, right? And I think that's a fairly common thing to do as well. More questions about boosting? All right, so just to give you a little bit more intuition, I wanted to give a toy example. This example uses AdaBoost, which is slightly different from the LogitBoost variant that we just derived. So here's our initial classification problem, right? Some pluses and some minuses. And if we train a decision stump on this, we might get this, right? Where we'll get a couple of the pluses and separate them from all of these guys over here. And here I've circled the training errors, right? And so what will happen now is we'll make another distribution where these circle points have higher weight, right? So that's given by the size of the symbol, and then everybody else has lower weight, right? And if I train on this, I might get a classifier, right, that goes like that. And in fact, oh, actually, looks like it's getting this classifier next. And so now all of these minuses are wrong, right? But these pluses are right. So we reduce the weight on the pluses and increase the weight on the minuses. And these guys, we've gotten them right twice, so their weight is tiny. Same thing with these guys, right? The two minuses on this side. And so the most important ones are these guys, right? And now if we classify this, we'll get something where we separate those the big pluses and the big minuses, right? And we won't pay so much attention to these other guys. And now at this point, if we vote these three classifiers together, we get a decision boundary that looks like this, a stair-step function that's perfect on the training data, right? So that's what a run of boosting would look like, except that typically you'd have hundreds or thousands of them, much larger training set, more than 2 attributes, right? But this is sort of the toy example. All right? All right, so we've covered now 2 methods, boosting and bagging, both of which give us a way to get voted decision trees, as well as voted anything else, but let's compare them for voting decision trees. And so the idea with boosting is that you'll learn a lot of small trees, right? Each individual tree is supposed to be a weak learner, and so it can be pretty small, whereas with bagging, you're going to learn many large trees, right? Each tree is supposed to be a full classifier. With boosting, because you're changing the weights of the examples, each tree is going to fit a different part of the target concept, right? Whereas with bagging, each tree is going to fit the same target concept with just a bootstrap resample, right? So a slightly different weighting, but it's only sort of random noise that causes the variability among the trees. The goal of voting in boosting is mostly to reduce bias, right? To increase the expressivity, to get a voted classifier instead of just a single classifier. Whereas with bagging, you can think of it more as variance reduction. We're averaging over a bunch of bootstrap resamples, and so we're getting rid of the variance in the, or some of the variance in the training procedure. And both of them tend not to overfit. With bagging, the reason is that you're doing this bootstrap averaging, and so you're not using the full power of the voted hypothesis space, right? You're fitting the same concept a bunch of times and averaging together. And with boosting, the explanation that's usually given is the margin, right? So you get, they're sort of similar on the, at a high level. They both give you a way to get voted decision trees, but the details are actually fairly different between the two of them. They get qualitatively different sorts of votes. Okay. And just, oh yeah.
So if I do the bagging and resample with a probability that give higher probability to those points that predict wrong, then it will be set as boosting.
Right, right. So in bagging, ordinary bagging, you would make bootstrap resamples of your training data, so independent of whether you were getting examples right or wrong. If you modified that to make each bootstrap resample depend on all of the previous ones and favor the points that you were getting wrong, it would suddenly turn out to look a lot like boosting. That's a good point. And then just one more, take this comparison with a grain of salt, as with all comparisons, but I took this from Elements of Statistical Learning by Hasty, Tibshirani, and Friedman. This is 3 different ways of getting a vote. They tried bagging, which is the gold line. They tried a random forest, which is bagging plus the attribute, selecting only a subset of the attributes for each tree, and then they tried boosting. And on this particular data set, this is the test error. It went down to the lowest level for boosting, then random forests, and then plain bagging, right? But I think this is moderately typical, but you could see a different ordering in your own data set, right? And the other thing, by the way, is that the trees are the same between these two, the same size, but they're much smaller here. They're only 5-node decision trees in the boosting. All right, and this was for a spam classification problem, in case that matters. All right, so yeah, go ahead.
Boosting seems to be too good, so what have shown that?
Right, boosting seems too good to be true. A lot of people had that opinion when it first came out, right? It seemed almost miraculous, and there was a lot of research into sort of could we explain why it was performing well and under what circumstances it would perform well. So one thing that boosting will sometimes have problems with is if your training data is extremely noisy, right? Like if you have label noise where there's a, something that is incorrectly labeled positive among a huge pile of negatives, right? Boosting is going to get you to label that training point positive. And so it'll carve out a tiny little area of positive in the sea of negative, and that's probably wrong, right? So it tends to perform poorly, especially the original AdaBoost, right? Because it gave you an exponential penalty for getting things wrong, right? It tends to perform poorly when you have lots and lots of label noise.
So that means overfitting?
Yeah, right. So that's an example of where you can get it to overfit, right? Where as you boost, it's jiggering the decision boundary enough so that you're carving out a little area of positives where there should be none, where you should be smoothing over the label noise. The other thing that, I mean, it's expensive, right? You know, you're doing 500 or 5,000 of these classifiers, right? So, you know, that may not be a problem, or it might. These days, you know, not so much of a problem where you can have big server farms, but that is a problem. And the other thing that is, you know, sub-miraculous about it is the interpretability, right? You start with a very interpretable class, decision stumps, and you boost it together, and, you know, who knows what it means, right? You have 5,000 rules telling you conflicting things. So, you had a question as well?
Yeah, it seems to me that like with weak classifier, you get better.
Right. So with the more noise you have, the weaker you probably want your classifier to be.
If I understand correctly, random forest have weaker classifier than that.
Oh.
Boosting have weak classifier.
Right, so it's not the weakness in random forest so much as the extra variability that's introduced. Right, so I don't know if anybody actually knows the true answer for why random forests work well with this sort of, but the heuristic explanation that I usually think of is that, well, decision tree fitting is NP hard. And so if you do something that knocks you into a different local optimum, then that probably is helpful, right? So I think of the subselection as a way of getting sort of additional variety as a way to push yourself out of local optima. I don't know if that's right or not, but that's the way I usually think of it. Okay, cool. So hidden Markov models and dynamic Bayes nets. So in some sense, this section is completely useless in the sense that it follows directly from stuff you guys have already learned, right? So you guys have done Markov random fields, you've done factor graphs, you've done Bayes networks, and all of this actually just follows from all of that. But you know, because of the difference between P and NP, right, it's much easier to verify a proof than it is to come up with the proof yourself. It's actually, you know, useful to go through this special case because it's one of the most common special cases of Bayes nets that you'll run into. So the goal of these things, of these models, is basically inference over time. So here's a simple example of an inference over time problem. You have a robot whose true state is its xy position and its orientation theta. So theta is between minus pi and pi, and x and y are real valued. It has controls, let's say its velocity and its angular velocity. So you can tell it how fast to go forward and how fast to turn. And it has some sensors. Let's say it has n range sensors, where what a range sensor does is it tells you the distance to a landmark. So think like an RFID tag, right? So you can get an RFID tag reader, and you know, you say, okay, interrogate tag number 237, and it'll tell you what is the time of flight for a radio signal between me and tag number 237, which you can translate into a distance, right? So what you'd like to do is figure out where is the robot and where are the landmarks, right? So that's a good inference problem. You can write down a model, right? This is sort of the standard model for a robot this way, right? You know, so the increment in x is your velocity times the cosine of your heading, right? That sort of thing. You know, the details of these aren't so important, just so long as you can write down an expression for what the time evolution looks like. And I guess the point of this is partly that, well, it's not a linear model, it's not convex, right? It's got a bunch of trig functions and other nasty stuff in it. So if you run this model without observing any, if you run this model without observing any, come on. Technology is wonderful. Hello? There we are. All right. So as I was saying, if you run this model you get something that looks like this, right? So this is just the robot wandering around, just to give you an idea of what the model looks like. And the goal then is going to be inference over time, right? So what I'm showing here are samples from the posterior as we run the robot around for a while. There's one sensor, which is at the center of the screen, and we're repeatedly observing that the range is 1 meter plus noise, right? And so if you keep observing that, the robot must be going in a circle around the sensor. And so that's what this is showing, right? So let me show that again, right? So we start off with some fair bit of uncertainty, and as we keep observing, we get tighter and tighter clustering around being a meter from the obstacle, right? All right, so that's our goal. And in order to do this, well, we can put together a factor graph, right? And so our unknowns are the position of the robot at step 1, position of the robot at step 2, at step 3, and so forth. And this factor graph is interesting because it has regular structure, right? So what, each of these factors, so this factor here, right, it depends on your current position and your current controls, and it affects your next position. This factor here depends on your current position, and it affects your current observation, right? And in general, we're going to have a factor graph that looks like a single structural unit repeated over time, right? So we have in this example here, right, the structural unit is something like this, right? This is our unit, and we've just carbon copied it 3 times and connected it up together, right? So in general, we're allowed to have any structural unit as our time slice, and we're allowed to make connections between any adjacent time slices. Conceptually, it's infinite off to the right, but in practice, we cut it off at some maximum time. And then the factors have to be conditional distributions. In other words, for this factor, it has to sum to 1 over all possible values of x2, y2, theta 2. Right? And so what that gives you is what's called a dynamic Bayes network, right? And you can run all of the things that we talked about a few weeks ago on a dynamic Bayes network. For example, you can run belief propagation to figure out conditional distributions, right? So in particular, there are 3 kinds of variables. We have observation, state, and controls. So these guys are observed, these guys are observed, these guys are hidden, typically. And so the typical inference question that we'll ask is we observe something about these observation variables, we pick some control variables, and we want to know what is the state. Okay? So that's what I said, condition on them. When you condition on them, they basically disappear as arguments of the factors. And now we have just a chain-shaped factor graph. All right? So just to show you what the algorithms look like on this, I'm going to work with a very simplified version, which has just 3 discrete states and 2 discrete observations, right? And no control. In other words, just one choice of control, keep going forward. And so when you do that as a factor graph, it looks like this. And this particular type of dynamic Bayes net is called a hidden Markov model, right? So you have one observation variable, one state variable, and they're connected across adjacent time slices, all right? And we can write down potentials, right? So this is the conditional probability of xt plus 1 given xt, right? The conditional probability of yt given xt. We can do something like condition on observing HHL and ask a question like, what's the marginal probability of the second state variable, right? And I'm not going to go through this, but this should all look fairly familiar, right? We just write down the potentials. Here, what we've done, this is the H column, right? So here, the H column here of this potential, H, H, and then the L column, 2 copies of the potential connecting states. We can, again, I'm not going to go through the actual math, but we multiply together potentials, sum out the nuisance variables, and in the end get to something that looks like this, which is our distribution over the second state variable, right? So this, in the context of a hidden Markov model, is called the forward-backward algorithm, right? So the forward-backward algorithm is just belief propagation. You pass messages forward in time, starting from the beginning of time going to the end. You pass messages backward in time, from the end of time back to the beginning. And then in the middle, at any given state, you have one message from behind and one message from ahead, and you multiply them together, and you'll get the distribution over that current state, right? So it all follows from what you've done before, right? But it's worth looking specifically at this, this case because it's a very useful case. And so I said that. And the summary is basically, well, what I said already. Just a really useful special case of Bayes networks. Right? So any questions about those? Hidden Markov models or dynamic Bayes nets? All right, cool. So that was the very fast version of hidden Markov models. Approximate inference. Okay, so a lot of the time when you're doing inference in, let's say, log linear models, exponential families, factor graphs, right? Some of these models that we've told you about, a lot of times you have a large tree width, you have high arity discrete variables or even continuous ones, and so you can't afford exact inference. In particular, the normalizing constant that you would need in order to make exact inference is the integral of some difficult function over a high dimensional volume. And what do I mean by a difficult function? I mean that most of the contributions to the integral are hidden. So you have very tall, narrow peaks, which you can hide very well in a high dimensional space. And the solution to that is numerical integration. And so there's a bunch of numerical integration techniques, and I just wanted to quickly go over a few of them. And again, the goal of this section is not necessarily to give you a full course on numerical integration techniques, because I think there is, in fact, a full semester-long course on numerical integration techniques. I just want to show you what are sort of a few of the main concepts, so that if you need to do it, you sort of know where to start. So the sort of problem I want you to imagine is something like this, right? So this is a grid map. So the variables are for every, I think, 3 centimeters square of the map, is it occupied or unoccupied, and what's the probability of that? This is of a particular building that somebody was actually able to do a pretty decent job of tracking what is the posterior distribution over the map by just driving a robot around and observing it, which I don't know if you've ever tried to do something like that, but it's hard enough to do, just get a halfway decent looking map, but to be able to actually track, some decent approximation to the posterior for something at this high resolution with this accuracy was actually a pretty impressive technical feat. If you want to see how they did it, the citation is off here at the bottom right. Sort of more generally, we typically have all of this comes down to Bayes rule, right? Everything at its base is just Bayes rule. So if we have some parameters theta, in that case it was the map, but in other cases it might be the parameters of a logistic regression or something else like that. We have some data that we've observed, and Bayes rule tells us the probability of the theta given d is d given theta times p of theta over p of d. Usually the prior p of theta is a pretty simple function. Usually probability of data given the parameters is simple, except that it's not pre-normalized, right? So it might be given by a factor graph in which we have to compute the normalizing constant before we can use it. So this thing will be simple. This thing will be simple up to a normalizing constant. That's a normalizing constant, right? And so what we have is that p of theta given d is proportional to, I guess I should say, zp of theta, p of d given theta, which we can compute, and p of theta, which we can compute, right? And so the problem then is going to be, we have these two things we can compute, and in order to actually use them, we have to be able to do an integral over a very large high-dimensional volume of something that looks like this, right? So is everybody with me on what the problem is that we're trying to solve? Yeah, okay. And just to point out, the same thing is true for discriminative learning, right? So this here was a generative model, probability of data given your parameters. But if you have some conditioning variables x and observed variables y, you can do essentially the same thing. It'll be proportional to a normalizing constant times the conditional probability and the prior over your data, right? And so the sort of thing that you can do with this, right? This is just a very simple logistic regression problem. Happens to be the Fisher-Irish data, where your conditional probability of y is a sigmoid of a linear function of your input, and your input has a normal prior on both parameters, right? And if you write it down, this is what the expression looks like. And then if you take a sample from the posterior, it looks like all of the blue x's, right? And so you can see that it's kind of an interesting distribution. It's not it's not just concentrated around a point. There is some uncertainty in both of the parameters a and b, and there's correlated uncertainty, right? So if you increase b, you tend to decrease a. So that's kind of interesting. And our goal then is to be able to get something like an approximate sample from this posterior, which we can use then to do things like calculate the normalizing constant, or we can use it to get what's called the predictive distribution, right? So what we would like to do is get the probability of y given x, right? So we have some inputs and we want to predict the probability of our output. And by the law of total probability, we can just stick in a theta and then integrate that theta out. Then we can use Bayes' rule to put the theta on the other side of the conditioning bar. By assumption, theta and x are independent, so you just get p of theta here. And then here, what we're going to do is, if we can sample a bunch of times from p of theta, right, this is the expectation over the distribution p of theta of this thing, right? And so this is the predictive distribution for a single theta. And so if we can get a sample here, we can approximate this integral by the sample average, right? Because this is just an expectation, and we can approximate expectations by sample averages. All right, so if we can get a sample from the posterior like this, then we're basically done. And in this particular example, so I want to point out that this here, right, that red x is the maximum likelihood estimate for this particular logistic regression problem. And it's not actually very typical of this distribution, right? It's sort of off to one end of it. And even though there are samples here, they're sort of thin, right? Like there's a little bit of a tail here, but the distribution is definitely skewed away from the maximum likelihood estimate. And so there is really a true benefit to knowing this full distribution instead of just getting the maximum likelihood estimate. And you can picture it better by looking at the predictions we're going to make, right? So what I said was to get the predictive distribution, we take a bunch of samples from the posterior, we do the predictions with each of those samples, and we average them together. So that's exactly what I've done here. I've taken a bunch of sample parameter vectors. Each of these lines corresponds to one sampled parameter vector. And then the predicted y given x is this sigmoid function for each one of those parameter vectors, right? And so you can see there's sort of a green band, and the approximate predictive distribution is the average of all of these green samples. And so you can see in the middle, this red curve, which is the maximum likelihood, is a pretty decent approximation of the middle of the distribution over green lines. But over at this edge, right, the maximum likelihood is very atypical, right? It's sort of predicting too certain, right, too close to 0 and 1 compared to the bulk of the predictive distribution. All right? And so it actually really makes a difference to have the full posterior instead of just approximating it with the maximum likelihood estimate. So this is actually a pretty typical case. The sort of typical way in which maximum likelihood fails is to be too sure of itself. Like it should be admitting variability in the parameters. It should be integrating out uncertainty in the parameters, and instead it's predicting just one. If you have a lot of data, this isn't a problem. We know theoretically that that has to be true because of the Cramer-Rao theorem. But of course, if we have tons of data, well, we're never in that situation, right? We should be so lucky as to have tons of data. So what do we do to get that sample from our posterior? The typical example is Markov chain Monte Carlo, or MCMC. And let's take a look at what that looks like. So we have an integration problem, right? This was the integration problem I wrote before, is that we have maybe an unnormalized probability of y given theta of an x and a prior over theta. And so we have some function which we're considering a function only of theta, and we want to normalize it to make it a probability distribution. And the hard part is the integral over theta. And so what we'd like to do is search for areas of high contribution to that integral, right? So in other words, they are, there are high contributions to the integral that are hidden somewhere in this high-dimensional volume. We'd like to run some kind of a search algorithm to find it, right? Where we know a bunch of optimization algorithms, so maybe we can use them to find areas of high contribution. But just naively running a search procedure and looking only at those is going to be, well, it would bias our estimates, right? We would get, our search procedure would sort of focus on one area and would have poorly characterized behavior. So what do we do? I guess there's two answers. One is if we have a good guess ahead of time where we might find areas of high contribution, well, if we know a distribution ahead of time that's likely to sample from areas of high contribution, we can use that distribution to sample, and then because we know the distribution, we can try and correct for the effect of the bias. I'm not going to show you how to do that, but examples of algorithms that do that are importance sampling and particle filtering. So they're fairly well-known algorithms. This example that I gave you before of the posterior from, right, this example of the posterior from the sensing, that was actually gotten using a particle filter. All right. But the other thing, what I want to focus on, is what's called Markov chain Monte Carlo, which is suppose that we can't guess ahead of time where to find the areas of high contribution, right? Then what we're going to do is design a randomized search procedure that tends to increase the integrand, r of theta, if it's small. And there are a couple of famous Markov chain Monte Carlo procedures called Gibbs sampling and Metropolis Hastings, which I'll give a quick overview of in a couple of slides. But then how are we going to use it? We're going to run this search procedure M for a while, and we'll take the resulting point that it finds as our sample. And then we're going to try and calculate what is the distribution that results from this randomized search procedure. And so the trick is in being able to design a randomized search procedure where it's possible to calculate this distribution. And in particular, what you'll get is the distribution of theta is what's called the stationary distribution of our search procedure. So what is a stationary distribution? Let's take a look. Right? So for any hidden Markov model, or a dynamic Bayes net, or really any procedure where something random happens over time, you could run it for a long time, stop at a random point, and then pick a sample, right? And so what I've done here is I've taken our robot and I've just run it for a very long time, right? And you can see that very quickly you get sort of, you don't know how long ago you started, right? You just get to a, right? So at the beginning, it's sort of a, it's clear that you're near the beginning. But after a little while, right, you get to this sort of uniform distribution of robots across the state space, right? And this is what I mean by the stationary distribution. right? So you don't know, the stationary distribution is basically if you run it for long enough that you don't know, have you been running it for a long time versus a really long time, just by looking at the samples, then you've reached the stationary distribution. And so our goal is going to be design, is to be able to design a Markov chain Monte Carlo search procedure which has a specified stationary distribution. In other words, we're given this R of theta, this integrand that we want to integrate and turn into a distribution, and we want to design a randomized search procedure for areas of high R of theta such that the stationary distribution of this search procedure is in fact this desired distribution that's proportional to R of theta. Okay? So I'm seeing confused looks. So let me step back and start from the beginning. Okay, so we have, we want to do Bayes' rule, right? So Bayes' rule, we get some distribution, right? Some formula for our distribution that looks like this, right? Something where we have something we can compute that we have to normalize in order to make it into a distribution. So in order to do that, that's a computationally difficult problem. The reason it's computationally difficult is that this integrand here, this R of theta, is going to be very peaky, and theta is typically a high-dimensional parameter. And so it's going to be hard to find areas where R of theta is high. And that's going to make it difficult to get an accurate approximation of the integral. And so what we'd like to do is design a search procedure that finds these high R of thetas. And the Markov chain Monte Carlo methods that I'm about to talk about are ways to design such a search procedure so that we can actually characterize what is the distribution of thetas that we get out at the end of this search procedure. Does that make sense? Okay. Cool. And so the way we're going to use this search procedure is, in particular, the search procedure is going to be designed such that if you run it for a long time and then stop and take the resulting theta, the distribution of that theta that you get is actually going to be R of theta over a normalizing constant, right? So you're given this function R, and you're able to design a search procedure such that its stationary distribution is R of theta normalized, right? So that's good, right? Because it lets you then just get a sample, for example, from your posterior. And if you do it a bunch of times, it lets you get a bunch of samples from your posterior. Okay? So the way it works, it's pretty simple description. The difficult part of it is in proving that it works, which is the sort of thing I always like, right? It's a very simple procedure to run, and it's just the analysis that is hard, but somebody else already did the analysis, so we can take advantage of that, right? In particular, these guys named Metropolis and Hastings. So the way it works is that we start from an arbitrary point, theta, so an arbitrary parameter vector. We repeatedly tweak our parameter vector to get another one we'll call theta prime. And the way we tweak it is called a proposal distribution. So the idea is that we're proposing, if we start here, we're proposing to move to this other vector. And then we decide whether or not to accept, right? So we accept the proposal if it does move to an area of much higher R of theta. We reject it if it moves to an area of much lower R of theta. And in between, we randomize according to a formula that is not particularly enlightening, but you can look it up if you need to use it, right? But basically what the point is that the formula approaches 1 if you move to an area of very high R of theta, and it approaches 0 if you move to an area of very low R of theta. And the probability that you actually accept is called the acceptance rate, unsurprisingly. And then you just run this, right? So it's a really simple algorithm schema. And our freedom in applying it is just selecting what is this proposal distribution. After we select the proposal distribution, everything else is, has been worked out for us, right? And so a typical example of a proposal distribution would be just a small Gaussian perturbation to your parameter vector. So if you do that, you get an example like this, right? So I started here at this red circle. I made a proposal to move the parameter here. Oh, I should say, what does this plot mean? So the background here is r of theta. Blue areas are low r of theta. Red areas are high r of theta. And so I'm simulating a run.
So r of theta is the distribution of theta without normalization.
That's right. R of theta is your unnormalized posterior, right? And so I'm trying to sample from that, from r of theta over a normalizing constant. And so what this demonstration is showing is that, in fact, Metropolis Hastings succeeds in getting sort of a random walk through areas of high r of theta, right? If you work out the math, you will be able to convince yourself that, in fact, it is actually exactly going to sample from r of theta. But what the example shows is just that, well, yeah, it succeeds in getting you to an area of high r of theta. Okay.
So after this step, you will sample one theta.
Right, exactly. So you could run it for a long time and sample one theta, and then run it again and sample another theta. What people actually do in practice is they'll take multiple thetas from a single run, which is okay as long as your run is long enough, right? And so in practice, what people will do is they'll try to get diversity in starting points, and then take multiple thetas per run for efficiency, computational efficiency. But notionally, you just run it for a long time and you take the theta, then you run it for a long time and you take the theta. Right, so this is computationally expensive. It's a good way to burn lots of processor cycles. But it's important because it's a way that people do burn lots of processor cycles in order to get a more accurate answer, right? So you're trying to get, instead of just maximum likelihood answer to your logistic regression, a sample from the posterior over your weight vectors. All right, so going back to this example, right, so this is just an example run of Metropolis Hastings. I started at the red point. I proposed to move here to this parameter vector, and it was accepted, right? It proposed here, it stayed here some number of times, then proposed to move here, right? And you can see that sometimes it does move down. It moves to low areas of lower r of theta, which it has to in order to be able, for example, to reach other modes. But it sort of does a random walk. This is a very short run so that you can actually see it. If I ran it for a long time, it would cover this area and spend most of its time here, a little bit less of its time in this smaller mode, a little bit less of its time in this even smaller mode, right? So that's sort of what a run of Metropolis Hastings looks like. More questions about the example? Yes?
So the argument was you don't move unless you actually increase r of theta.
So if you increase your r of theta a lot, you always move. If you decrease it a lot, you always reject. But in between, you randomize. And so you might move down a little bit. And even if you go up, you might not accept, right? So there's a formula which, again, my recommendation is just to look it up rather than, there's no point in my putting it on the slide unless we were going to do the math.
But by that, though, you're only taking large steps for large increases then? Small steps if you're going down?
No, it's not the length of the step that matters, right? It's the amount of increase or decrease in your, right? So, yeah. I mean, it's you should rarely be taking steps that go down a lot, but you will sometimes take them. You should frequently be taking steps that make you go up, but you will sometimes reject them. All right. And then once we have our samples, right? So we run this for you can think of it as either running it for a very long time and taking the last sample, or what people actually do is they'll run it for a very long time and then take every sample after a certain point, right? And the idea is that there's this sort of burn-in stage where you're not sampling from the stationary distribution, but then after you've mixed, right, which is not a discrete thing, you haven't, mixed or not, you've just, gotten closer to or farther from the stationary distribution. But after some time, you say, I'm close enough to the stationary distribution, and I'll take all of the samples. And then you might do this a bunch of times, right? Start from a bunch of different points, discard a burn-in range for each of them, and take all of the samples after that. And then we can estimate, for example, the normalizing constant in our posterior by just taking the sample average. Or we can estimate the predictive distribution the same way I described, right, by taking the sample average of the predictive distribution for the individual samples theta. Okay. So the important thing for getting a good Markov chain Monte Carlo algorithm is getting a good mixing rate or a good mixing time. The mixing time is basically how long do I have to wait until I get a highly accurate sample from the stationary distribution. Mixing rate is 1 over that. What matters to get a high mixing rate? Basically, for Metropolis Hastings, what matters is to get a good proposal distribution. Right? So what you would like to do is to get a proposal distribution that moves you around quickly, right? Because that's going to let you explore regions of high R of theta very quickly. But you also want it to stay within the regions of high R of theta. You don't want it to often propose to you to go to a really bad place. Right? And so the optimal proposal distribution would be just to sample from the posterior. Then you would accept every time. And you would mix in one step. Of course, if you could do that, you wouldn't need Metropolis Hastings, right? But that sort of gives you an idea what a good proposal distribution is. More generally, what you want to do is sort of have a good, like what people aim for is to have a good approximation to a fairly large local region of the posterior, right? So if you can make, for example, some distribution that fits well to the shape of the posterior over a fairly decent size area around your current theta, then that'll be a pretty good proposal distribution. And of course, what people often do is they'll just propose a Gaussian tweak, right, like a small Gaussian jump, and that can mix really slowly, but it's a good fallback to know about. So the last thing that I wanted to mention is a special case of Metropolis Hastings, which is often used in practice, and it's called Gibbs sampling. And the way it works is that you have a parameter vector theta, right? And it's equal to, theta 1, theta 2, theta 3, and so forth, where each theta 3 is a whole block, right? So I'm going to say is in R K3, right? And this here is in R K2, right? And so the idea is, right, you've got a parameter vector divided into blocks of parameters. And what Gibbs sampling is going to do is going to pick a block uniformly at random, or it turns out you can use other schedules too, but let's just say uniformly at random. And then it's going to compute the conditional distribution of that block of parameters given all of the other parameters, right? So you have a current value of theta. You leave all but one block fixed. You condition on those values of those parameters, and you compute the conditional distribution of the remaining block. Right? So Gibbs sampling only works if it's easy to compute that conditional distribution. But for example, if you have theta being described by some crazy big factor graph, right? Then what you can do is, well, your factor graph can extend off into the distance in many directions. But if you condition on, here's theta 1, theta 2, theta 3, theta 4. You condition on theta 1 through 4, that's enough to get the distribution of theta 5. It'll just be basically the product of all of the factors that connect those existing ones. And so if you're only normalizing over a small dimensional subset, you can actually perform the normalization and then resample from theta. And so, saying that again, Gibbs sampling is for a parameter vector divided into blocks. What you do is you fix all but one block, compute the conditional distribution of that remaining block, and sample from that conditional distribution. And it turns out that this is an instance of Metropolis Hastings. Maybe not obvious that it is. And also, if you go through the formulas, it's got an acceptance rate of 100%, which is nice, right? It means that the higher your acceptance rate, the faster you mix, all else being equal. And so people were very happy when they came up with this variant of Metropolis Hastings that always accepted, and also has a fairly simple form. Again, I'm not going to go through the proof of why it always accepts, but it's pretty easily available. You can find it out on the net. So questions about what Gibbs sampling looks like? Yeah. Right, so as with any search procedure, you can get stuck in local optima. It's sort of soft getting stuck. So what actually happens is that you never are completely stuck, right? There's always, because you can prove that Metropolis Hastings does mix, does eventually have its stationary distribution equal to the desired distribution, it's always possible to get out. But the typical way of getting stuck, let's say you have you're proposing a Gaussian tweak to your parameter vector, and you're in a region of really tall peak with really deep valleys on either side. Then you'd have to accept a bunch of moves moving you down, right, in order to get across the valley and back into a lower peak over on the other side. And that is possible, but it might take a very long time. Right, it's the sampling that gets you out of the local optima. And it gets you out in only a very weak sense, right? So these Metropolis Hastings procedures, they are a blessing and a curse for machine learning. They're a blessing because it's a set of cranks you can turn that give you a way to sample from an arbitrarily complicated posterior, right? They're a curse because they can have mixing times. They can get stuck in local optima in the sense of it would take you 1 billion years ever to sample out of it, right? And they never tell you when they're stuck, right? They're just, I'm running. I know I'm eventually going to get to the stationary distribution. No, I can't tell you whether I'm there yet. Right, so there are a whole lot of papers which have the flaw, okay, we sampled from something we think is the posterior distribution, but we have no way of telling you that it actually is. Right? So, yeah, very useful, but it has its flaws. Yeah?
I guess the way to get out of the local optimum is
The way to get out of a local optimum is what?
we have multiple stuff.
Right, so multiple restarts will help you get out of local optima. So will a good proposal distribution, right? So if your proposal distribution can propose leaping across a valley, right, then it's not going to be so hard, right? If you can do quantum tunneling through the area of low energy, right, then you're going to be able to get out of this local optimum. But of course, saying that that's a good idea is very different from actually being able to achieve it. Right, so for some distributions, you can get a good fast mixing Gibbs sampler or Metropolis Hastings sampler. For others, it's much harder to get one that mixes fast. So that was the end of what I wanted to tell you guys today. And since it's the end of the last class and we have a few minutes left, are there any questions about anything throughout the course that I can answer in 5 minutes? No? All right. Well, it was great to teach you guys. I had a lot of fun. I hope you had fun and learned something too. And we have the final project reports are still due, and if you signed up for the extra credit, those are still due in a little while. But other than that, you guys are close to off the hook. See you next semester. Thank you.